Okay, hi Nidir. Uh, we'll continue with chemistry now. We have discussed redox reactions in the past where we are discussing both oxidation and reduction happening at the same time. Now we're going to change a little bit of gears. We're going to cover equilibria or equilibrium. Uh, it's an interesting chapter. It's a very different kind of chapter to chemistry, but it's very important to chemistry. We'll talk about the very details that happens. So yeah, let's get started. We'll talk about it in great depth. The book I was reading through a book, it actually does a good job to explain the concepts in the chapter. So wherever you are stuck, whenever you're stuck, I'm basing this discussion all on a book. Feel free to definitely go to your book, stop, and then look at things again. Right? All right. Fine. So let's get started. I'll keep referencing your book the in the middle of this thing. So just keep this thing. So okay, let's talk about what equilibrium is. So mostly we know that what happens is two things react to give you C plus D, right? This is what we know normally that happens, but we see that sometimes it does not happen like fully. Right, so we think that if A and B you keep in a container, then you'll get C and D, right, at the end. But then maybe you expect that there will be some A and B. One of the example that a book gives here again is something of CuSO4. So CuSO4 plus H2O, this hydrated copper sulfate, if you heat it, which is blue in color, then it becomes white in color later. And then of course, like the water evaporates, but if you add the water back, then it again turns thing. So this is kind of like a so it happens in a forward reaction when heat is applied, and so this thing can also go in reverse direction, right? So this is what. So this is first of all what we call a reversible reaction. So let's keep talking about these things. So first reaction. First we're talking about a reversible reaction. Reversible reaction. Right. So the idea is that it can go one way and it can also go other way. Right. Then we talk about okay. So next is the concept of what we're talking about. Say that A and B are given, then you get C and D at the end. So the idea is that you might not get all of C and all of D. Meaning that say you put uh, 1 mole of this, 1 mole of this. You expect 1 mole of this and 1 mole of this to be found, but maybe say only 0.6 moles of this and 0.6 moles of this are found. And so out of this, not the whole 1 mole is consumed. 0.4 and 0.4 is only used up. Right? Sorry, 0.6 is used up, which went to the other side, but 0.4 is there. So you say that there's a concept called yield. Yield is a percentage, is the amount of product. So product can be C or D, any one of them, that you have gotten by amount of product expected, right, into 100%. So if you're in this case, the example that we discussed, the yield was 60% because it was 0.6 and then we expected 1 to be formed, and so then that in percentage terms will be 60%, right? So just to be precise, it to 100% like that. So in this case, the yield would be 100%. So we say that okay, there are some reactions in which we expect 100% yield, but they are not a 100% yield. So we say that yield is not equal to 100%. Then it's called an equilibrium reaction. That means the reactant is forming the product, but the product is also forming the reactant. So the yield is kind of so you can say that maybe try to push it this way, but then some of them wants to recombine back to A and B. So it is an equilibrium reaction. It is an equilibrium reaction, right? Okay, so let's try to. So the way it is written is with these half arrows, C plus D, right? So in a practical example that your book talks about is H2 in gas format plus I2 in gas format reacts to give you HI and also gas format, 2 of HI in gas format, right? So in this case you try to make HI, you not all of it combines, but there are some left. Okay. Now we talk about the basic ideas of. I'm again following just your book. I'm just following the characteristics of equilibrium. So the first thing it is dynamic. So dynamic is a very important concept. Dynamic is does not mean that okay, if it has to give 60% yield, that means 60% of the reactant combines to give 40% product done. Like it stops reacting, this is formed to nothing happens. No, not like that. Constantly there is H2 and I2 trying to form HI, and HI is constantly breaking down to give you H2 and I2. So it's like a constant thing. At some point, initially H2 and I2, there's a lot of H2 and I2 forming at some point. So at this point, H2 and I2 forming is high at the initial time, and then maybe after some time it reduces. On the other hand, the breaking of HI current increases. So there is no HI in the start, so let's actually make it 0. At this point it is 0 and then it rises up and then it joins this guy. So this is the kind of the rate. This is the rate of HI breaking, and this is with time. Then it flattens out, and the black guy here is the kind of rate of H2 plus I2 combining. So in some sense, that the black one is the forward reaction, and the lower one is the backward reaction. So you can see that H2 and I2 forming to this guy is the forward reaction, which is the red guy or the black guy, and then the reverse is the blue guy that we are talking about here. So we see that initially the rate of blue is 0. That means there is no HI breaking because there is no HI to be formed. But you have some H2 plus I2 that starts making HI. So slowly the concentration of HI rises. So there is some backward pressure. And at some point it happens that you have. So we can also say this as maybe. Yeah. So this is like at some point at the end H2 and I2, the amount that they want to combine to give HI is the same as HI wants to break. At that point, it settles out. And you can imagine that at this point, at the final point, you have both HI and H2I2 in the mixture. So initially, just to be clear, you had H2 and I2, which is what you wanted to react. Finally, you have H2, I2 and HI. All three. You expected only HI to be there, but H2 and I2 are also there because HI wants to break down into H2 and I2, right? And of course, these HI and HNI are probably less than what you started with. So you can imagine that instead of starting the thing from having H2 and I2, in other scenario, maybe I could have started with just HI at the start instead of H2 and I2. Right? Then at the end, would have H2, I2 and then HI. And of course, in this case, the HI concentration would decrease instead of HI concentration would be increasing. So in that case, the graph would look something like this. So the blue curve will be at the top. So HI concentration is high and then it settles down to a value. And the black curve is at the bottom. So you have 0 concentration H2 and I2. But then as soon as the HI is breaking, this concentration rises and then settles to a value. At that point, the reaction is kind of complete, right? And so now this next point that I want to bring up, which your book talks about, is this concentration at the end and this concentration at the end. Let's mark it maybe in a different color. Maybe let's mark it in green. This concentration and this concentration right here are the same. So they are kind of constants. So let's see. So your book talks about two graphs. So now these are not in terms of rates, but these are in terms of concentrations. So we see that there is one reactant that is there who breaks down, and then other concentration that increases, and then both of them settle to a value, right? So this is maybe the concentration of H2 and I2. This is the concentration of HI, right? And then in other scenario, you have too much of H2 and HI, which starts to break down, and then as a result, the H2 I2 concentration rises and settles to this value. So we see that this value 0.683 is the same. So you can have a high H2I2 concentration to start with, and then it decreases, or you can have no H2I2 to start with, but instead have HI. So HI will decrease, and then it settles down. But in this case, HI was increasing. But both of them settle to a same value. So important to understand this thing. Right, so the second property that we are studying here is, I'm just going in the order of your book. At equilibrium, forward is equal to forward rate of reaction. Oh my god, okay. Let me just restart. My Jamboard crashed. Okay, at equilibrium, forward rate is equal to backward rate, which of course that we talked about, that the rates become same. And then finally we said that concentrations at equilibrium are independent of initial conditions in a way. Like whatever you initially put, the finally it will be the same. Right? So this is what we talked about. Okay, and the last thing is a moot point in the sense that it should be a closed system. Closed system meaning that say you start to remove the product as soon as it is formed. So you're forming HI, there's some way maybe you can remove HI. If you keep removing, then there will be no backward pressure. There will be nothing that converts back to H2 and I2 because whatever HI you are generating is being taken away. So you want to have a closed system in which nothing goes away. Closed system as in whatever is generated stays within that vessel, within that container. So maybe you can imagine that there are two solid reactants that are reacting to give a gaseous product. If there is a open container, then the gas might escape and might not reform the solid that are there. But if the solid and the gas is locked in a container, then maybe the back gas can convert back into solid and solid can convert into gas or something like that. So the closed system requirement must be there to make an equilibrium. So this is the basic thing, right? So let's keep going now. So let's talk about how to change the position of equilibrium. This is a very important idea. Okay, so I'll simplify this. So what does this mean? Maybe you want to say that, okay, you have 60% yield, right? You want to increase the yield, meaning that you want to have more of the product or you want to have less of the product, right? So that is changing the position of the equilibrium. So if you change the yield to 70%, that means that there is more of the reactant. That means you have shifted the equilibrium to the right. So again, keep this picture in mind, A plus B is C plus D. So if you increase the concentration of C plus D, that means of course this will go down. Then you have shifted the equilibrium to the right overall. Okay, similarly to the left, that means more reactant, less product. Okay, so how do we change this position of the equilibrium? Right? So there was a guy called Le Chatelier who is very important here. So let me just see his spelling properly. Okay, so Le Chatelier's principle. Okay, so what did he say? Right, so it said that whatever way the equilibrium changes, So first of all, he said that it changes because of three things: pressure, temperature, and more importantly, concentration. So we'll talk about it in opposite order actually. These two are important. So this one is only valid when there is a gaseous reactant or product. So that is kind of will be the special case. This one is valid for we'll see. We'll go into detail, but the last two are important. So he said about these three things: if you try to change the pressure for gaseous reactant in the product, if you try to change the temperature, and if you try to change the concentration of the reactants, then the position will either shift to the left, the equilibrium position will shift to the left or to the right. So this is the basic idea. Now, in which direction does it shift? That was his principle. That is what he said. That the equilibrium will move to minimize the change. So whoever has caused that change, it wants to minimize. So we'll see exactly what that means. This might be confusing, but it will become clearer as we go on. Okay. So let's see. Okay. So first things. So let's first discuss. Number one is concentration. So first of all, the concentration ka unit is moles per liter, right? So it is how many moles are there in a liter, or also which is same as saying a moles per dm cube, right? 1 liter is 1 dm cube. So you should remember this conversion always. So which is equal to 1,000 cm cube. And the internal conversion that's going on here is this. So you should always remember this. Okay. Okay. So let's keep going. So, and another thing that we'll mention concentration like this. So this means the concentration of H2 as a gas maybe is 0.2 moles per dm cube. So this is the representation we'll use. This square bracket will mean the concentration wherever we talk about. Okay. Okay. This will come in handy later, but for now just keep it in mind. Okay. So let's discuss this example that your book is talking about here. So it's saying that look at this reaction. So it's saying that there, first of all, it's an equilibrium reaction. We see this symbol in the middle, right? So we see that ethanoic acid and ethanol are reacting to give ethanoate. So acid and alcohol is giving you an ester and water. So this is the esterification reaction that we had previously looked at. So we know that this gives the ester, and ester plus water also breaks down to give you acid and alcohol. So it's saying that what happens when we increase the alcohol? So there is a change in the concentration. So Lee Chatelier says that we want to minimize that change. So if the alcohol has increased, if we move the reaction to the right hand side, if we produce more product, then the reaction of ethanol will decrease. The reaction of the amount of reactant will decrease. So you want to decrease the concentration of this gas, so you move the reaction to the right. Just follow the words. Okay, what happens if we add more water? So if there is water, there is more product, then you want to move the reaction to the left so that the concentration of the product decreases. So you of course, and then what happens when you remove some water? If you remove some water, then you want to fill that up again, as Lee Chatelier says, then you want to move the reaction back to the right. So just follow all of this once. Okay. Okay. Next we'll talk about, so this is about concentration. Next we'll talk about pressure. So pressure ke liye the important thing is there should be an unequalness in the balancing numbers on both sides. So if you look at this example, SO2 and O2 are reacting to give you SO3, and but this SO3 also wants to break down to produce SO2 and O2 at the same time. Hence this is an equilibrium reaction. Okay, so we look at these numbers. So it seems that there are 3 moles of gases, 2 of this and 1 of this, which are combining to give you 2 moles at the end. So 3 moles gives you 2 moles, and then 2 moles goes back and gives you back 3 moles. So if you now increase pressure, right? So this imbalance first of all is important. So if there is no imbalance, if the moles are same on both sides, then if pressure will have no impact. Okay. And the other thing is that reactants have to be gaseous. So these are gaseous moles only. Okay. So now we are saying that in this gaseous medium, say you're trying to push a piston in. So there is a container and then you're trying to put a pressure in. So to decrease, so now the pressure inside has increased because now it's in a tighter space, right? So what they want to do is they maybe want to decrease their number so that they can move around freely. So that means when you increase the pressure, they want to decrease the number. So decreasing the number in this particular reaction happens when they go to the right. Then that means this will be more formed. So the number of moles will decrease. So the pressure again will be released, will be lessened. So of course, mind you, in this reaction, there is higher number of moles on the product side. But it could happen that there were 3 moles of gas is producing 4 moles. Then in that case, it would shift to the left. So there will be less SO3 that will be formed. In our case here, there will be more SO3 that will be formed, but in that hypothetical example that we're talking about, less SO3 will be formed. Okay. So what happens if we increase the pressure? It goes to the right. It will use more reactant moles, as there are 3 reactant moles. It will try to decrease the number of moles according to Le-Chatelier's principle, and it will form more SO3 at the end. If you decrease the pressure, opposite happens. Okay. And the last thing that we're going to talk about is temperature. So temperature, the important thing is you want to know whether the reaction is endothermic or exothermic. So endothermic is when you have a positive delta H. So delta H is the heat released in the reaction. If it is positive, that means it is endothermic. If it is negative, then it's exothermic. It gives out reactions. So that means, so if you look at this HI thing again, so when HI goes to H2 plus I2, it absorbs energy. It absorbs some energy, right? So that is what we want to talk about here. Okay. So now if we increase temperature, that means surroundings has a lot of temperature, so it wants to consume that temperature. It wants to reuse up that energy so that the temperature of the surrounding comes back to normal, right? So how will it consume temperature? When it goes to the right, when there's more H2I2 will be formed, that means more endothermic reaction will take place. That means more absorption will take place. So the increase of temperature will shift the reaction to the right because the reaction was endothermic. If the reaction was decreased, if the temperature was decreased, then it would move to the left. And moving to the left will make the reverse side of the reaction exothermic. It will release energy, so it will try to raise the temperature of the surrounding area. So again, this Le-Chatelier's principle, it tries to oppose the change, whatever externally has happened. Okay, the last thing that we talk about is catalyst. Do catalysts change the left or the right? It does not. It only helps you get there faster, whatever that equilibrium point is. Okay. So just make this point very clear. So let's just summarize all of this once. So we talked about concentration. We said concentration of reactants or products if it is increased, then the reaction goes to the left. If it is increased of the reactant, right, then the reaction goes to the right. So the next thing that we talked about is temperature. So temperature, if it is increased, then and for a delta H that is negative, that means it is exothermic, right? Then the reaction will go which side? Take a minute to think about it. It's exothermic reaction and temperature is increased, right? So temperature is increased, so it wants to consume the temperature, and if it is moving to the right, that means it will release more energy. So we don't want to do that, so it will move in the opposite way. So that it is endothermic in the reverse direction. So like that. Of course, opposite is understood. For pressure, the important thing is we checked that there should be number of gaseous moles on product and on product slash uh, this thing on the reactant side should be different. So this is the important thing. If they're different, then if the pressure increases, then the equilibrium shifts to the side of the lesser number of moles. So if the reactant has lesser number of moles on the product side, then the reactant will go left. If product moles are less than reactant moles. Again, all of these are gaseous moles. And the last thing is catalyst that we talked about has no effect. It only gets to the equilibrium faster, it does not move it to the right or the left. Right? What that means, it does not change the concentration of the products or the reactants. It only like if the normal reaction happens in 5 minutes, it will make it happen in maybe 1 minute. Okay, cool. Okay. So let's keep going then, if this is clear to you. Again, this is a little bit of an involved chapter, so just like stick with it as much as you can. Okay, so the final equilibrium thing is represented by an equilibrium. So we have an equilibrium constant, which is called Kc. So Kc is nothing but, so if we talk about this H2I2 giving you Hi, so the first thing that you want to do is balance that. So now put the number 2, and then what you want to do is so equilibrium constant Kc is defined as nothing but the concentration of Hi square, because there is a balancing number 2 here, divided by the concentration of H2 and concentration of I2. So that's it. So you want to take the ratio of these, and so the idea is that this ratio never changes. So something like, so let's take a book's example right here. So again, so this is that same thing. So the square up top, and then you just take H2 and I2 concentration on the bottom. So they say that okay, they have done the reaction for different so different H2 and I2 concentration at equilibrium. So they saw that in one H2I2 concentration over 0.68, then this was 0.86764. Similarly, if they started with 0.5, then the concentrations were this. Then they had different concentration at equilibrium for H2I2, then the final concentration was this. For in each of these cases that we have tried to find this ratio, Hi square by H2I2 key concentration, then you'll always get the number 161. So this is the idea. So 161, 159, 161, 161. So this is the idea that the whatever concentration you have, it will roughly come out to the same constant of that reaction, so to speak. I hope that is clear. Okay. So this is of course independent of the concentration. Like if you add more of this, then more of this will be formed, but less of this will be consumed, and it balances out. Okay. And one more thing to consider here, we ignore the solid components here. So if there is a reaction with something like this, so aqueous, and then Ag and Fe, we see that okay, when we write the equilibrium expression, then first of all because all of the numbers, balancing number here are 1, so there are no powers anywhere, so 1 1 1 1. And the next thing that we want to see is, because one of them is solid, that then we don't mention it in the equilibrium expression. So we only mention for anything that can have a concentration. The solid cannot have a concentration, right? Solids is very dense. So but then a liquid has, or an aqueous solution or something has a concentration. So how many moles or something did you put in that liquid? Something like that. So say the aqueous ones have. So of course then we ignore the solid and this equilibrium expression. Definitely go through these sums. The in unit sums will be easy, and then go through that. So in this you have to be careful about who you are booking. For gas you can take it. Okay, so this is good too. So basically you don't want to take pure form. things, okay, concentration. So a pure solid item is just called a solid, a pure thing is called a liquid, right? So that you also don't want to take. Aqueous and gas are fine because they diffuse with each other, so that's okay. Okay, so this is good. Okay, so the next thing, so for we talked about Kc here, which is defined in terms of concentrations, right? Uh, so we of course talked about how Kc does not change when the concentrations are changed, right? So if you increase the concentration of product, there is more product formed, but the equilibrium when it finally balances itself, there'll be it will balance itself in a way that Kc remains constant. So how we said that, okay, in this thing you maybe added, so it was balanced here you saw. Okay, then you maybe added a little bit of I2 at the start, so that maybe ended up consuming a little bit of this, and then it produced more of this. So something like when you still take the ratio, it will be the same. So yes, so Kc does not change with concentration. Similarly, Kc does not change with pressure, and Kc does change with temperature. It does. So you need to have different Kcs at different temperatures. So when you specify Kc, you will always specify at what temperature you are specifying. Okay. So this is fine if we get this. Then the other alternate concept that we define is a Kp concept, which is this concept of so just not concentration but something called partial pressure. So let's first look at what is partial pressure. So if there are two gases in a container A and B, maybe like there is a total pressure of 11 pascals here, but then maybe 3 pascals is because of one gas molecule and 8 pascals is because of another gas molecule. So the partial pressure we say because of gas A is 8, partial pressure because of gas B is 3, and the total pressure because gas A and B is 11. So just this concept is of partial pressure. So of course total pressure is equal to partial pressure of A and partial pressure of B. So this is an expression that we need to remember. Okay. Then we talk about how Kp can be now defined not in terms of equilibrium but in terms of these partial pressures. So again, there is a square of partial pressure up top because there is a 2 here, and then there will be a cube here because there is a 3 here. And then there's a 1, so this is the 1. So in terms of partial pressure, if you can find these out at equilibrium in that container, again, all of this is only valid for gases. So in that equilibrium condition, when the equilibrium has been reached, you measure the partial pressure due to ammonia. As I said, at the end, you might have started with just N2 or H2, or you might have just started with a lot of NS3. But at the end, when the reaction comes to a conclusion, nothing more is happening. Then there will be all three NS3, H2 and N2 in the solution mixture, right? So at that point you want to measure the partial pressure of NS3, partial pressure of H2 and partial pressure of N2. That will make the total pressure, and those partial pressures you want to put in this formula and then find Kp, something like that. So of course this units will not be moles per decimeter as we discussed, which is the unit of concentration. The unit of this will be pascals, which is the unit of pressure. So then of course Kp can have different units. In this case it will be Pascal square by Pascal to the power of 4. It will be, so at the end it will be 1 by Pascal square. So Pascal to the power of -2. So in this case, in this reaction, it will be Pascal square by Pascal to the power of 1. So it will be just be Pascal, as they say. Of course, just follow all of this. You need to also be able to write the units of Kc and Kp for different reactions at different times. So this is all covered in your book. Definitely go through it. Just keep doing all these sums, all the internal ones you need to do for this. It's a easy chapter, but you need to just go through them once. Okay, and the last thing that you talk about is you can define in terms of mole fractions also. So you can say that here instead of, you can say there are 8 by 10, there are maybe 8 moles of this, 3 moles of this, and total there are 11 moles of gases present here. So in terms of number, if you count, maybe like you can find the ratio uh, in terms of mole fraction also. So mole fraction is what? So mole fraction is nothing but total number of moles of one gas by the total number of moles present in all of the gases. So maybe you have 0.5 moles of this, and then so you have 0.5 of this, maybe 0.9 of gas B and 0.6 of gas C. So in this case, you can find the mole fraction like this, and whatever this mole fraction is into the total pressure will give you the partial pressure due to only one this thing. So you can find out like this also. So if you're given maybe the total pressure and you are given the number of moles of three gases, then you can find the partial pressure due to H2, partial pressure due to I2, and then partial pressure due to HI. Then put all of that in the formula for Kp, which will be dependent on the reaction. So you need to be careful of the balancing numbers, and then trying to find what is the Kp value. Again, all of this is given in your book, of course. Try to follow it step by step. Okay. So one or two applications in this area is like similarly we want to do ammonia production. So ammonia production we know is a reversible thing when you try to combine this in N2 and H2. This is called Haber's process. So in this, if we try to apply Le-Chatelier's principle, we say that okay, so is this reaction endothermic or exothermic? Okay, it is negative, so that means it is exothermic. That means it is energy is released. So what you want to do is you want to decrease the temperature as much as possible so that it will go to the right. It will release as much energy from the reaction to compensate for the cooling. So that's what you want to do. So you want to decrease the temperature. That will increase your yield of ammonia, right? So you want to take care of. So you want to decrease the temperature. That is number one. Number two, you can do is increase. So what can you do in terms of pressure? So you see that okay, all of them are gaseous, so that is good. Next, you want to see what are the reactant moles. It is 1 plus 3, so that's 4 moles on the reactant side, and then there are 2 moles on the product side. So now you say that you want to increase pressure because that will make the whole equilibrium move to the side of the lesser number of moles, which is the product side. So you'll have more ammonia towards the end. So you don't want to decrease the pressure, but you want to increase pressure and decrease temperature. So these are the two things. So this is how you increase yield. And the last thing is, of course, they're saying if you don't make it a closed system and you start removing ammonia by condensing it into liquid, maybe somehow by boiling point properties or something that you can condense ammonia out. That means there is no ammonia that will convert back to N2H2 because as soon as it is being converted, you are just siphoning it out. So that means there is no backward force on the reaction. So it will go to 100%, near 100% yields. So that's good. So you want to remove the product as much as possible. So that will these three things together will increase the yield of ammonia. So you want to think about all of these things. Okay. So similarly, this thing right here, you can follow it. What happens in this reaction if we increase the pressure? I'll just tell you the answer. It will move to the right. Take a moment to think about it. Okay, what happens if we decrease the temperature? Again, just giving you the answer, it moves to the right. Try to think about why that is. Again, if you're not able to follow, you can talk about it, or it's also given in the book. Okay, so the last thing that we'll talk about, I think in this chapter, yeah, this is the last thing, is the acid-base equilibria. So in this, we'll take a little bit of D-root. We'll talk about what acids are, and then we'll talk about how the acid-base equilibria is affected. Okay, so the first thing what is an acid? Acid is something that has a pH below 7. So anywhere between 1 to 7 is acid, then 7 is neutral, and then 7 to 13 is base. Like that's how we talk about it. Then one other thing that we know is there is something called a neutralization reaction. If you add an acid to a base, then at some point salt and water is formed, right? So all this we know. So one of the first, when people were thinking about acids, the first time that they tried to define an acid, they said whatever can neutralize a base to form salt and water is an acid. So if you have a base already, you just try to put different substances in it. One of them neutralizes it. You call whatever neutralizes it, you call an acid, right? So they want to maybe then started defining acids in a broader way. So of course, so examples there some are HCl, HNO3, H2SO4. These are all inorganic acids. But then you have some organic acids which have, of course, carbons in them, so you call them organic acids. So benzoic acid, ethanoic acid, acetic acid, and stuff like that. Acetic acid is nothing but ethanoic acid. Okay. So they want to then broaden the definition of what an acid is. So they tried calling acid something that releases hydrogen plus ions. So if you see that when you add HCl in water in an aqueous solution, then you see that H plus ion is formed, right? So it is releasing H plus. So then you call whatever is donating releasing H plus is called an acid, right? Then the next thing that they want to talk about, then how do you define bases? So they say that some bases, not all bases, all acids release hydrogen ions, but some bases dissolve in water to give you hydroxide ions. There are so if you look at these bases example, then there are some oxides, and then there are some hydroxides, and then there's also this ammonia, which looks a little different, right? Now, if you think about it, which of them, when dissolved in water, will give you hydroxide, which is OH minus, at an output? If I ask you, if you think about it, so it looks like these two will not be even able to give OH minus because they don't have an OH minus to give. But these two can give, which is true. And but what about this guy does not even have an O? How will it give an OH minus, right? So it looks like these two are alkalis, what we call bases that are soluble in water, because they already have an OH minus and they can give an OH minus just easily. So they are called alkalis. They are easy, like we can easily fit them in. But then other ones, let's see. So this one NH3, when we add it in water, it actually makes its own new compound called NH4 plus and OH minus. The good thing, so the bad thing is it reacted in a way with water. The good thing is it gave an OH minus. So we can still call aqueous ammonia an alkali. So ammonia is the gaseous form, and then when you dissolve it in water, it becomes an aqueous solution. So that gives an OH minus. So that's also an alkali. So these three are sorted. About these two, they are just bases. They are not alkalis. They are not soluble in water. So we can't define. We can't. So in our definition of something that releases H plus or releases hydroxide, these we can't call them bases yet. Okay. So then let's go to the third theory. So the first theory was whatever neutralizes acid, base is an acid. Then we defined acids as hydrogen ion donators and then bases at OH minus donator. So at H plus or OH minus donators. And then the third thing that we talk about is the Bronsted-Lowry theory, which does not require this presence of this aqueous medium. It just says that whatever gives H plus is an acid, which is the same as what we had already discussed. H plus is a proton. So proton donator is an acid. But the base end is different. It does not say it is OH minus donator, but it says that whatever is an H plus acceptor, whatever is a base. So let's see how that is. So in this case, we see that when HCl is dissolved in H2O, then the H plus of HCl goes to the H2 and forms something called a hydroxonium or a hydronium ion, right? So it forms this guy. So what happened there is the H plus was given from HCl to H2O. So H2O here acted as a base and HCl here acted as an acid. It gave the proton and this accepted the proton in Bronsted-Lowry definition. So that is exactly what is shown here. So in a similar case, if you look at this aqueous ammonium formation, this H plus now goes from here to this guy, and this guy accepts an H plus to form this guy. So in this case, this is the base. So that extends, that is consistent with what we were discussing earlier. So NH3 is the base, and this is the acid here. So funnily enough, what we see here, in this case, H2O was accepting the H plus, so it was acting as a base. In this case, H2O was donating the H plus, so it's acting as an acid. So we say that whatever, there are some things in this world that can act both as an acid or a base depending on context. So they are called amphoteric oxides. So these H2O, so water is an amphoteric thing right here. So if you look at this guy here, which is so this is called chloric acid, HClO4. This is the name, and when which reacts with the weaker another acid, an ethanoic acid. You see what happens. The stronger acid wants to give its H plus more than the weaker acid wants to give its H plus. So at the end, because of the presence of a stronger acid, it has to succumb to the powers of the stronger acid and accept the H plus given by the stronger acid. So this H plus goes from here to the smaller, to the weaker guy, and the weaker guy has to accept. So the weaker, even though it's an acid, in this particular reaction, it's acting as a base. So we need to understand this. So of course, because the accepting tendencies of this are not very high, that means the yield in this reaction will be pretty low, which is why this is an equilibrium reaction, right? So just an intuition. So you need to remember all of this. Okay, so they are saying that some reaction don't go to completion, of course, like this one, right? Okay, now in the Bronsted-Lowry definition, we can define something called a strong acid or a weak acid. So we can say that if it completely tries to give a lot of protons very quickly, so if you take a specific concentration, in this case you have taken 0.1 moles per liter of HCl, then you will have 0.1 moles per liter of hydronium, of hydroxynium, right? Of this H3O plus. So that means that all of HCl, what you had put in that water, all of that has dissociated to give you hydroxynium. So that's the meaning of a strong acid. But for weaker acid, this is not the case. You maybe put 0.1, but you only say got maybe a little less, you got maybe 0.69 or 0.5, right? So that will be a weaker acid. So we assign a number to it. We say that when all of it is dissociated and when 0.1 is achieved, then it's called a pH of 1. So this has a pH of 1. But then when only not all of it is dissociated, maybe 0.5 is dissociated, then it has a pH of maybe 2.9, a little higher. So the strongest acids get the lowest pH, which is 1, and then weaker acids kind of go up. So on the base side, it will be the opposite. So if you put an alkali, take an alkali and put it in water, the amount of OH minus if you get, if all of the alkali breaks down to give you all of the OH minus, so if you say maybe put 0.1 moles per decimeter of alkali, decimeter cube of alkali, then it gives you 0.1 moles per decimeter cube of OH minus. That means all of that base has dissociated. So what I'm saying here is, if whatever you have taken, if it has given you the same concentration here, that means it has the pH of 14, which is the other side of the spectrum. And for weaker bases, it will not give you fully, so it will be a little less. So it will be maybe 12 or 10 or something like this. So you need to remember this in your head. Okay, so we understand this. So the last thing that we talk about here is this idea about distinguishing a weak acid from a strong acid. So of course you can say that how to identify a weak from a strong is just check the pH values, right? So that's a one thing. So the way that you check it is, you might have done this in your lab. You have a pH indicator, which can be a universal pH indicator. It's called pH paper. You must have done it in your labs. So either that, or it can be something like a pH electrode where you put it in the solution and it just gives out a reading. Okay, this is the pH level. So it's not like it's more electronic and it's better. The other thing that you can do is you can measure electrical conductivity. Now, because the high strong acid solutions have a lot of dissociation, have a lot of hydronium ions that are formed. So they will always have high conductivity as compared to weaker acids, which are partially dissociated, right? So there are fewer ions that are there, so that will have poorer conductivity. So again, point to remember: strong acids, high conductivity. And the last thing is the reaction with the reactor metals. You know that Mg and Zn these reactions will react with very strong acids to give you some bubbling in the form of this hydrogen gas that's released. So if you have an acid, just try to dip a magnesium ribbon into it and then see how much bubbling is happening. If a lot of bubbling is happening, that means it's a strong acid. This reaction is highly promoted. Okay. Now for the very last topic of this chapter, which is an easy one, we talk about indicators and titration. These things I know that you've done in your lab, so I'll just go through them very quickly. So of course, we have indicators which show you whether it's an acid or a base, right? So of course, so if you have an acid, if you have an indicator, it kind of has two forms. So it has a dissociated form and it has an undissociated or an unionized form, right? So if this is ion stands for indicator here and H stands for an acidic component and H a hydrogen in that indicator, then the unionized form will look like HIN, and the dissociated form is that H plus breaking away and ion minus breaking away, right? And this, of course, is the equilibrium reaction. So the indicator itself in the itself is in a equilibrium reaction. So how do we shift the side of the indicator? We just say that okay, if it's in an acidic environment, the indicator, that means there will be a lot of H plus, right? Because acid will itself give H plus, then the indicator will try to move it towards the left by Lee-Chatterjee's principle because it wants to minimize the effect of having that extra H plus. So that means there will be a lot more of HIN than ion minus. That means say if both sides say are colored, this is color A and this is color B, that means in an acidic environment you will observe color A. Similarly, if the environment is basic, that means this H plus ions will be completely removed and will be they are proton acceptors. So this is getting removed, so it has an incentive to produce a lot more of it. So the indicator will move towards the right, producing a lot of color B. This is how when you put an indicator in a acidic or a basic solution, it changes color. This is how you know. Okay. So this is what they have talked about methyl orange, like which pH ranges where which indicators work best. Okay. So this setup of titration, you know, I'm not going to go over it. So, but the basic idea is you start from a base at the bottom and then you have a lot of acid at the top and you slowly start adding acid slowly, drop by drop into the base. At some point, the neutralization reaction happens and it's exactly at 7. And then very quickly after that, you continue to add base. So the overall solution becomes acidic. So it starts from a complete basic solution, then becomes a 7 neutral, and then goes towards an acidic solution. So now the last thing that they talk about here is this combination of a strong acid, like a strong acid with a strong base. So it will be very high when it starts, like something like 13, and then very quickly it falls as soon as you stop adding, like it touches 7 in the middle, and then it becomes acidic very quickly. So you want to choose an indicator which can reflect this change. And of course, different indicators change in different range. So for phenolphthalein is pink when it's basic, and then in after 8.2, it's still basic. But then if it is once it crosses the 8.2 thing, it is basically colorless. So this kind of an indicator is good. You will know this change properly. So in the bromothymol is also good here. So you can choose either one of them. So strong acid, strong base, we are good. Then now let's look at strong acid with weak base. So weak base means that instead of starting at this 13 ka heights, maybe starts at 11. And then it's very like damadol, right? It's like you start adding acid, it decreases a little bit. But then as soon as it neutralizes completely, then it sharply falls back to number 1. Like which was here, because it's a strong acid still, right? In this case, I wouldn't say that an indicator like phenolphthalein is as good. Maybe because maybe it changes at around 8.2 we saw. At 8.2, maybe it can change a little too quickly before the neutralization has happened. So you want it to change in this area. So maybe a bromothymol here is a good option in this case. Okay. Then the opposite case, weak acid with strong bases. So strong bases, you start with 13, keep on adding acid slowly, and then it fatafat changes, but then it does not drop down to 1, it stops at somewhere here, and then it gradually increases because it's a weak acid, right? So again, just things to know. And then weak acid, weak base is the worst because it's just shaky in the middle, and then there's a very small change at the neutralization, and then it's shaky afterwards. So it's very difficult to determine exactly when uh, the titration or the neutralization has happened. But yeah, so what can we do? Okay, and so one of the exercises here, you should definitely try to do all 22 questions. One of the exercises here is what happened here. Was it a strong acid to a strong alkali? Like what is being added to what? Were you adding acid or were you adding a base? And what you were adding to was a strong component. What you were adding, was it strong? So these are the things that you want to think about here. Okay, so I'll stop here. This is a complicated thing, but just read through the book. Your book is very well compiled in this area. Whatever doubts you have, we'll discuss. Just do all the 22 sums that are mentioned internally. Okay, cool. Bye bye.